Scaling a digital product from a local machine to a global distributed architecture requires managing millions of concurrent requests, petabytes of data, and hardware that is constantly degrading. Traditionally, we learn to build these systems in isolated silos. Most computer science curricula separate relational databases, operating systems, networking protocols, and programming languages into distinct tracks. This fragmentation forces engineers to learn different vocabularies to describe what are often identical concepts. A database uses strict concurrency control to prevent transactions from colliding. An operating system uses a lock to keep two processes from writing over each other's memory. While the terminology differs, both rely on the same underlying mechanism, isolation. System architecture consists of a finite set of cross-cutting design principles that recur across every domain. Identifying these patterns allows a solution used in database design to become an immediate blueprint for solving problems in networking or distributed systems. Professor Joy Arulraj proposed a way to map this shared vocabulary by constructing a periodic table for computer systems. To qualify for this table, a concept must be abstract, functioning independently of specific technologies, and general, appearing across multiple different computing domains. These principles are organized into thematic groups, such as structure, efficiency, and reliability. The structure group defines how we carve a system into parts and connect them through clear boundaries. The efficiency group focuses on doing less work or doing it cheaper by focusing effort where it pays the highest dividends. The reliability group includes the principles that keep a system correct despite hardware faults and partial failures. This table provides a shared vocabulary that helps engineers reason about architecture and trade-offs before they write a single line of code. System structure begins with the reality of human cognitive limits. A single mind cannot reason about a massive monolithic system all at once. Butler-Lampson addresses this with the directive to divide and conquer. Modularity involves partitioning a system into cohesive units with minimal, strict interfaces. This relies on abstraction lifting, which hides low-level operations behind a high-level interface that only expresses the user's intent. These layers stack. A web browser operates on an OS platform, which operates on a hardware platform. Each layer acts as an abstracted foundation for the one above it. These interfaces allow separate teams to evolve parts of the system independently without breaking the entire architecture. Warning tone. However, a common pitfall is adding architectural layers or generalized services just in case. The principle of simplicity counters this by resisting premature optimization until evidence shows a clear benefit. Effective structure uses boundaries to protect developers from the underlying complexity of the system. The efficiency group treats system design as the management of physical resources, bandwidth, latency, and memory. Engineers use a resource calculus to determine if a design meets performance needs under optimistic assumptions. This leads to work avoidance, the understanding that the fastest way to process a request is to avoid it entirely. A clear example of work avoidance in practice is the Content Delivery Network, or CDN. When a user in Tokyo queries a central database in New York for a static image, the packet travels across the globe and back, incurring a heavy latency cost. Edge nodes placed geographically close to the user cache those static assets. The request hits the local node and returns instantly, which bypasses the central database query and avoids the work of a long-distance trip. This caching mechanism is a form of approximate design. Serving potentially stale cached data through eventual consistency is an intentional trade-off. It sacrifices real-time exactness to achieve global scale. Lampson organizes efficiency into the AID framework: approximate, incremental, and divide. Dividing workloads through sharding and concurrency uses additional hardware resources to lower latency for the user. Scaling successfully requires accepting good enough approximations to prevent critical bottlenecks. Reliability starts with the fundamental assumption that physical hardware will inevitably fail, and complex software will always contain hidden bugs. Fault tolerance is the practice of designing systems that continue operating in a degraded state instead of crashing completely. Systems achieve this through redundancy in space, using replication and consensus protocols so that multiple servers agree on the data. Redundancy in time uses retry loops and exponential backoffs to automatically attempt an operation until a temporary failure resolves. Reliability also involves human operations. specifically Site Reliability Engineering, or SRE. SRE balances the speed of new features against system stability by setting explicit goals with consequences. This slide shows service-level objectives, or SLOs. These track the actual customer experience rather than expecting 100% perfection. Dependability relies on architecting boundaries that allow the system to absorb partial failures gracefully. Principles like modularity, work avoidance, and fault tolerance form a unified grid of recurring patterns that govern how software functions at scale. Butler-Lampson uses the acronym STEADY to evaluate any complete system. A system should aim to be simple, timely, efficient, adaptable, dependable, and yummy. However, it is physically impossible to maximize all of these variables simultaneously. Increasing dependability through replication costs you efficiency in hardware and network bandwidth. Increasing adaptability through deep modularity introduces new interfaces, which increases latency. Effective engineering involves selecting the specific principle from the periodic table that solves a problem while deliberately accepting the associated trade-offs.
Enhance your coding skills with us. Don't forget to subscribe to Code 5 Food for the latest updates and tutorials.